You know, I've spent my entire life studying the smallest things in nature atoms, electrons, photons, and what I discovered is that the closer you look at reality, the stranger it becomes. Not strange in the sense that we simply don't understand it yet, but strange in a much deeper way. Strange in the sense that our ordinary concepts, the words we use every day, the ideas of position and motion and cause and effect that seem so obvious and reliable, these concepts simply do not apply. They break down, they fail. And that failure isn't a temporary problem waiting for a smarter physicist to solve. It's permanent, it's built into the structure of nature itself. Let me start with something that sounds paradoxical, because quantum mechanics is built on paradoxes. And if you're not disturbed by them, frankly, you haven't understood what we are saying. Here it is. The opposite of a correct statement is a false statement. The opposite of a profound truth may well be another profound truth. Think about that for a moment. In classical physics, in the physics of Newton and everyday life, contradictions are problems to be eliminated. If I tell you an electron is a wave and then I tell you it's a particle, you try to say I'm confused, pick one. Bohr, which is it? But nature doesn't let us pick one. Nature insists on both, and not in the sense that it's sometimes one and sometimes the other, but in the much stranger sense that it is both. Simultaneously, until the very moment you try to pin it down. And then, only then does it become one or the other. That's complementarity. That's the heart of quantum mechanics. And that's what I want to help you understand today. Now, I know what you're thinking. You're thinking, surely things exist in definite states whether we look at them or not. A chair is a chair whether you're in the room or not. The moon is there even when no one's watching. This is common sense. This is how we navigate the world. And you're absolutely right for chairs and moons, but for electrons, for photons, for the fundamental building blocks of matter, common sense is not just wrong. It's not even applicable. It's like trying to use a map of London to navigate Paris. The map is accurate, detailed, useful, but it's the wrong map. Our intuitions were built for a macroscopic world of medium-sized objects moving at moderate speeds. We evolved to catch antelope and avoid predators, not to understand atoms. So when we peer into the atomic realm, you'll be surprised that our concepts, which work so beautifully for everything else, suddenly stop making sense. Let me give you an example, the famous double-slit experiment, because it captures everything strange about quantum mechanics in one clean setup. Imagine you have a barrier with two narrow slits cut into it, and behind that barrier, a screen that records where things hit. Now, fire electrons at the barrier, one at a time. Common sense says each electron must go through one slit or the other. That's what particles do. They follow definite paths. They're in one place at one time. And if you actually put detectors at the slits to check which path each electron takes, that's exactly what you see. Each electron goes through one slit or the other, never both. Fine. But now remove the detectors. Just let the electrons fly through without checking which slit they use. What do you see on the screen? Not two bands corresponding to the two slits. You see an interference pattern alternating bright and dark fringes, exactly like the pattern you get when waves pass through two slits and interfere with each other. Waves go through both slits simultaneously, overlap and create patterns of reinforcement and cancellation, but we are firing one electron at a time. There's nothing to interfere with, so how does each individual electron know to land only in certain spots and avoid others? The only explanation is that the electron, in some sense, goes through both slits, it interferes with itself, it behaves as a wave. But the moment you try to catch it in the act, in the moment you put a detector at the slits to see which path it takes, the interference pattern vanishes. Now you get two bands. The electron becomes a particle. You see the problem now. It's not that we don't know which slit the electron goes to. It's that the question, which slit does it go through, doesn't have an answer until you measure it. Before measurement, the electron exists in a superposition of states, a kind of suspended reality where both possibilities are simultaneously true. The act of observation doesn't reveal a pre-existing fact, it creates the fact. And here's where it gets strange, because this isn't just about electrons. This is about the nature of reality. For centuries, we assume that the world exists in definite states independent of whether anyone's looking. Science was supposed to be the study of objective reality, what's really out there. But quantum mechanics tells us there is no really out there in the sense we thought. There are only potentialities described mathematically by something called a wave function, and these potentialities collapse into actualities when a measurement occurs. The wave function evolves smoothly, deterministically, according to precise mathematical laws, that's the Schrödinger equation. But measurement is different. Measurement is discontinuous, probabilistic, irreversible. Before you measure, the electron is in a superposition. It's described by a wave function that assigns probabilities to different outcomes. After you measure, one outcome happens, the wave function collapses, and the superposition is gone. You can predict the probabilities of different outcomes with perfect precision, but you cannot predict which specific outcome will occur. That's not ignorance. There's not a gap in the theory waiting to be filled. That's the theory. The theory says nature is fundamentally probabilistic at this level. Now, you might want to object. You might want to say, surely the electron has a definite position all along, and we just disturb it when we measure. This was Einstein's objection, actually. He believed in what we call hidden variables, unknown properties that determine everything in advance, so that the apparent randomness is just due to our ignorance, like rolling dice when you don't know the exact forces involved. But experiments have now ruled this out. Not experiments that might be done someday, but experiments that had been done repeatedly with exquisite precision. The violations of Bell's inequalities, the demonstrations of quantum entanglement over kilometers, the fact that quantum computers work, all of this confirms that reality at the quantum level genuinely doesn't have the properties we assume it should. There are no hidden variables determining the outcome in advance. The electron genuinely doesn't have a position until you measure it. And that's not a statement about our knowledge. That's a statement about reality. But let me be clear about something, because this is where people often misunderstand what I'm saying. I'm not claiming electrons are magical or conscious, or that reality is just a dream. I'm saying that our classical concepts, position, velocity, trajectory, are not fundamental features of nature. They're emergent, approximate descriptions that work beautifully at large scales, but fail at small scales. When I say an electron doesn't have a position until you measure it, I don't mean it's hiding somewhere. I mean the concept of having a position is something that only makes sense in the context of an interaction that establishes it. The electron has the potentiality to be found at various locations, described by a probability distribution, but being at a location is not a property it possesses independently. It's a property that emerges in relation to a measurement apparatus. And this isn't mysticism, this is forced on us by experiments. This is what nature is telling us. This brings me to complementarity, which is really the philosophical heart of the Copenhagen interpretation. Complementarity says that a complete description of quantum phenomena requires mutually exclusive but equally necessary perspectives. Wave and particle, position and momentum, energy and time. These pairs are complementary. You need both to give a full account, but you can never apply both simultaneously. If you set up an experiment to observe wave behavior, you cannot simultaneously observe particle behavior, and vice versa. If you measure position precisely, momentum becomes uncertain, not because you've disturbed it, but because the state itself doesn't have a definite momentum. Heisenberg's uncertainty principle, which says you cannot know both position and momentum with arbitrary precision, isn't a statement about measurement error. It's a statement about the limits of what exists. A quantum system cannot possess both properties simultaneously with perfect definition. Both descriptions are needed. Neither is complete. And that's not a flaw, that's the nature of reality itself. And let's try to make this more concrete, because I know it sounds abstract. Think about trying to describe a quantum system, say an electron bound to an atom. You can describe it as a wave function, a spread out probability cloud that tells you where you're likely to find the electron if you look. This wave description captures interference effects, tunneling, the discrete energy levels that explain why atoms are stable and why chemistry works. It's enormously successful. But when you actually measure the electron's position, you always find it at a point. You never detect a smaller cloud. You detect a particle. So which is it really? And the answer I'm giving you is that question is meaningless. the wave description and the particle description are complementary. Which one you use depends on the experimental context. If you set up an interference experiment, use the wave description. If you're measuring position, use the particle description. Both are correct. Both are incomplete. And you cannot combine them into a single unified picture because nature itself doesn't provide one. Now this might sound like I'm just giving up. Like I'm saying physics can't give us a complete picture, so we should settle for fragmented, contradictory descriptions. But that's not what I'm saying at all. What I'm saying is that the demand for a single, unified, observer-independent picture is a classical prejudice. It's what we expect based on our experience with large objects, but it's not something nature owes us. Quantum mechanics gives us a complete description. It tells us everything that can be known, everything that can be predicted, everything that can be tested. It's just that what can be known is less than we thought. Nature herself doesn't contain answers to questions like, which slit did the electron really go through when no one was looking? And not because we're too ignorant to find out, but because the question presupposes a reality that doesn't exist. The electron doesn't go through one slit or the other when no one's looking. It doesn't go anywhere in the classical sense. It evolves as a wave function that includes amplitudes for both paths, and only when you perform a measurement does it become meaningful to talk about a specific path. And here's what's so remarkable. This isn't just philosophy, this has been tested. Every computer chip in the world relies on quantum tunneling, a phenomenon where particles pass through barriers they classically shouldn't be able to cross, because the wave function extends into regions where classical particles can't go. Lasers work because of stimulated emission, a purely quantum process with no classical analog. MRI machines exploit quantum spin. Atomic clocks, the most precise timekeeping devices ever built, depend on quantum transitions between energy levels. GPS satellites wouldn't work without corrections that account for both relativistic time dilation and quantum mechanical effects in the atomic clocks they carry. This isn't speculation. This isn't abstract theory disconnected from reality. This is engineering. This is technology. This is the only reason your phone works, your computer works, your watch works. Quantum mechanics has been tested more thoroughly than any theory in human history, with precision down to parts per trillion, and it has never failed, not once. Every prediction it makes about what we can observe has been confirmed. And what it tells us is that reality at its foundation is not what we thought. So when people ask me, but what is the electron really doing between measurements? I have to say the question contains a hidden assumption that nature doesn't support. You're assuming the electron has a definite trajectory, that it's always doing something specific even when we're not looking, and that measurement just reveals what was already there. But that assumption is wrong. The electron is not doing anything in the classical sense between measurements. It's in a superposition of possibilities, evolving according to the Schrödinger equation. And doing something specific only becomes meaningful when you perform an operation that entangles your measurement apparatus with the system in a way that collapses the superposition. Until then, there's no fact of the matter, and that's not ignorance on our part. That's nature. But now consider the role of the observer, because this is where things get philosophically deep. When I say measurement collapses the wave function, I don't mean conscious observation by a human being. A measurement is any interaction with a macroscopic apparatus that amplifies quantum effects into the classical realm in an irreversible way. A photographic plate, a Geiger counter, a screen that glows when struck. These are measurements. Consciousness isn't required, but what is required is an interaction that establishes a permanent classical record. And this raises a profound question. Where exactly does the quantum realm end and the classical realm begin? At what point does superposition collapse into definite outcomes? This is the measurement problem, and I'll be honest with you, we don't have a complete answer. We have a practical answer when decoherence occurs, when a quantum system becomes entangled with its environment in such a way that quantum coherence is lost and interference effects vanish, we see classical behavior emerge. But philosophically, the boundary is fuzzy, and that fuzziness isn't sloppiness on our part. It's telling us something deep about the relationship between the quantum and classical realms. What quantum mechanics forces us to accept is that we cannot separate the observer from the observed, not in the naive way classical physics allowed. In classical physics, You can imagine yourself as a neutral spectator, recording facts about the world that exists independently of your observations. But in quantum mechanics, every act of observation is an interaction that changes the system. The measuring apparatus becomes entangled with what it measures. The observer and the observed form a unified whole, and you cannot meaningfully talk about a system as if it existed in isolation. It doesn't mean reality is subjective or the consciousness creates reality. That's a misunderstanding. What it means is that reality is relational. Properties aren't possessed by objects in isolation. They emerge in the context of interactions. An electron doesn't have a spin in a particular direction until you measure spin in that direction, at which point the interaction establishes that property. Before the interaction, it wasn't hidden, it simply didn't exist as a definite fact. And this brings me to what I think is the deepest lesson of quantum mechanics, something that goes beyond physics into epistemology, into the very nature of knowledge. For thousands of years we've assumed that reality exists out there, complete and independent, and that science is the process of discovering what's there. Quantum mechanics says not quite. What's out there is a web of potentialities, governed by precise mathematical laws, but actualities only exist relative to context of observation. Knowledge isn't the discovery of pre-existing facts, it's the outcome of interactions. And there are limits to what can be known, not because of our cognitive limitations or because we lack better instruments, but because nature itself doesn't contain the answers to certain questions. You cannot know both position and momentum with perfect precision because a quantum state cannot possess both simultaneously. You cannot know which slit the electron went through without destroying the interference pattern because going through a slit and showing interference are complementary aspects that cannot coexist. These aren't gaps in our knowledge. These are boundaries on what exists, as far as we can tell. And we've tested this extensively. The world is fundamentally uncertain at small scales. Not uncertain in the sense that we don't know, but uncertain in the sense that definite facts don't exist until interactions create them. Within the limits of observation, within the domain where experiments can be performed and predictions tested, quantum mechanics gives us a complete picture. It tells us everything that can be told. But what can't be told is constrained by complementarity, by uncertainty, by the inseparability of observer and observed. And far from being a deficiency, this is nature teaching us about the limits of what it means to exist, what it means to know, what it means to be real. I sometimes think about how strange this is. We started by studying the smallest building blocks of matter, thinking we'd find simplicity, find the fundamental pieces from which everything is built, and what we found instead is irreducible complexity, not in the sense of being complicated, but in the sense of being irreducible to simple classical concepts. We found that you cannot build an atom out of tiny classical billiard balls bouncing around. The atom is an inherently quantum system with discrete energy levels, wave functions, superpositions, and all the rest. And you cannot understand these features by breaking them down into smaller classical pieces. The quantum realm isn't just miniature classical mechanics. It's something fundamentally different, something that requires new concepts, new mathematics, new ways of thinking. And even then, even with all our sophisticated formalism, we run into the limits of language, because language evolved to describe the macroscopic world, and at some point you just have to accept that words like position and trajectory don't mean what we thought they meant. But let me ground this in something tangible again, because I don't want you to think this is all abstract philosophizing with no real-world consequences. Every single piece of modern electronics relies on quantum mechanics. Transistors, the fundamental building blocks of computer chips, work because electrons can tunnel through barriers in ways that would be impossible if they were classical particles. The fact that we can pack billions of transistors onto a chip smaller than your fingernail, switching billions of times per second with incredible reliability, is only possible because quantum mechanics works, and because engineers understand it well enough to design devices that exploit it. Semiconductors, LEDs, solar panels, all quantum devices. The laser, one of the most transformative technologies of the 20th century, is based on stimulated emission, a process that has no classical explanation. You cannot build a laser using classical electromagnetism. You need quantum mechanics, specifically the idea that photons are indistinguishable bosons that prefer to occupy the same quantum state, which allows them to amplify coherently. This is engineering built on the Copenhagen interpretation, built on the principles of complementarity and measurement and superposition. And it works. It works spectacularly. Every time you use a smartphone, every time you watch a screen, every time you benefit from medical imaging or precision measurements, you're benefiting from our quantum understanding of nature. And here's something even stranger to consider: quantum entanglement, which Einstein famously called the spooky action at a distance because he couldn't accept it, has now been experimentally confirmed beyond any doubt and is being used in practical technologies. When two particles become entangled, measuring one instantly affects the state of the other, no matter how far apart they are. Not because some signal travels between no signalers, but because they're described by a single unified wave function, and measuring one collapses the whole wave function, determining correlations that couldn't exist if each particle had independent properties all along. This isn't some fringe effect. Quantum encryption devices use entanglement to guarantee security in ways that are physically impossible with classical systems. Quantum computers, still in their early stages but advancing rapidly, exploit superposition and entanglement to perform certain calculations exponentially faster than any classical computer ever could. These aren't thought experiments anymore. These are technologies being built and deployed. And they work precisely because the world is quantum, because superposition is real, because measurement collapse is real, because reality at the fundamental level is not what classical intuition suggests. You see, quantum mechanics has given us something unprecedented in human history: predictive power down to the atomic scale with extraordinary precision, combined with deep philosophical humility about the limits of what can be known. We can calculate the image levels of hydrogen to 10 decimal places. We can predict the outcomes of scattering experiments, the lifetimes of excited states, the magnetic moments of particles, all with stunning accuracy. But we cannot tell you what an electron is really doing when you're not measuring it. And the theory says that question is meaningless. There is no what it's really doing independent of measurement. That's not a gap in the theory. That's what the theory is telling us about reality. And it's been right again and again for 100 years. Now, I want to return to complementarity one more time, because I think it's the key to understanding not just quantum mechanics, but the limits of human knowledge. Complementarity says there are properties that cannot be known simultaneously, not because of practical limitations, but because nature doesn't assign them simultaneously. Wave and particle, position and momentum, energy and time, these are complementary aspects of a quantum system, and a complete description requires both, even though they contradict each other in classical terms. You need the wave picture to explain interference and diffraction. You need the particle picture to explain localized detection and countability. Neither picture is wrong, neither is complete. And that's okay. That's how nature is. The insistence that there must be a single, unified, contradiction-free description is a prejudice inherited from classical physics, and nature simply doesn't conform to it. Both are true. Both are necessary. Neither is complete. That's it. That's complementarity. That's nature. And this has implications far beyond physics. If nature herself doesn't provide answers to certain questions, if reality is fundamentally contextual and relational, then perhaps we need to rethink what we mean by objectivity, by truth, by existence itself. I'm not saying anything goes or that reality is whatever we want it to be. That's nonsense. The mathematics of quantum mechanics is rigid, precise, unforgiving. It makes definite predictions that can be tested and falsified. But what it's telling us is that objectivity isn't quite what we thought. There isn't a God's eye view, a perspective from nowhere. It sees all properties simultaneously as they really are. There are only perspectives from somewhere, experimental arrangements that reveal certain aspects while necessarily leaving others indeterminate. And the collection of all possible perspectives, all complementary descriptions, gives us the fullest picture nature allows. But that picture is not a single snapshot. It's a multifaceted, context-dependent understanding that respects the limits nature imposes. I think what disturbs people most about quantum mechanics isn't the mathematics. The mathematics is actually quite elegant. But the philosophical implications, it upends common sense. It tells us that determinism fails at the fundamental level, that particles don't have trajectories, that properties aren't intrinsic but relational, that observation isn't passive but participatory. It tells us that the universe, at its smallest scales, is a place of irreducible uncertainty and complementary truths, where contradictions aren't problems to be solved but features to be accepted. And that's uncomfortable. We want nature to make sense on our terms. We want a clear, definite, observer-independent reality that we can map and measure and predict. And for large objects moving slowly, we get that. Classical mechanics works beautifully. But for atoms and electrons and photons, nature says, no, you don't get that. You get something richer and stranger and more subtle, something that requires you to abandon certain intuitions and embrace new ways of thinking. But here's the remarkable thing. Once you make that leap, once you accept complementary and measurement collapse, the rest, quantum mechanics becomes incredibly coherent and consistent. It's not a mess of contradictions. It's a beautifully unified framework that explains an enormous range of phenomena with a handful of principles. The Schrödinger equation governs how wave functions evolve. The Born rule tells you how to calculate probabilities. The uncertainty principle sets limits on what can be known. And from these simple starting points, you can derive the structure of atoms, the periodic table of elements, chemical bonding, superconductivity, and countless other phenomena. It all hangs together. It all makes sense. Not in the way classical physics makes sense, but in a deeper, more sophisticated way that respects the strangeness of nature, while still giving us extraordinary predictive power. So when people ask me whether quantum mechanics is true, I say it's the most empirically successful theory in the history of science. It has been tested in ways that would have been unimaginable to earlier generations, and it has passed every test. Not just approximately, not just qualitatively, but quantitatively, with precision that boggles the mind. The anomalous magnetic moment of the electron, for instance, agrees with experiment to 12 significant figures, 1 part in a trillion. No other theory has ever achieved that level of agreement. Quantum electrodynamics, the relativistic quantum theory of light and matter, is the most accurate theory humanity has ever devised. And it's built on the principles I've been describing: superposition, complementarity, measurement collapse, uncertainty. These aren't speculative ideas waiting to be confirmed. They've been confirmed billions of times over. They're solid as anything in physics. But does that mean we understand quantum mechanics? Well, that depends on what you mean by understand. If you mean, can we calculate outcomes, design experiments, build technologies, make predictions? Absolutely. We understand it better than we understand most things. But if you mean, does it fit with our pre-theoretical intuitions about how reality should be? Then no, we don't understand it at all. And I would argue that's the wrong question. The right question is, does nature fit with our intuitions? And the answer is no. Nature is under no obligation to make sense to creatures who evolved to survive in a macroscopic world of moderate speeds and medium-sized objects. The fact that we can grasp quantum mechanics at all, the fact that we can develop mathematical tools to describe it and experimental techniques to test it, is already extraordinary. But demanding that it conform to classical common sense, that's asking too much. That's asking nature to be something it's not. We are not observers standing outside nature looking in. We are participants. We are made of atoms governed by the same quantum laws as everything else. When we perform a measurement, when we interact with the quantum system, we're not revealing a pre-existing fact. We're participating in the creation of that fact. And that changes everything. It means physics isn't the study of an objective reality separate from us. It's the study of patterns in our experiences, predictions about what we'll observe under various conditions, relationships between preparation and outcome. It's more subtle than classical physics, more epistemologically sophisticated, more humble about its claims. But it's also more powerful, more comprehensive, more successful at describing the world as it actually is, not as we wish it to be. And perhaps that is the deepest lesson of all. Physics has given us power to manipulate atoms, split nuclei, create new materials, build quantum computers, but it has also shown us the boundary of what can be understood. Not a temporary boundary that will be pushed back by future discoveries, but a fundamental boundary built into nature herself. There are questions that don't have answers because reality doesn't contain the information to answer them. There are facts that don't exist until interactions create them. There are truths that are complementary, mutually exclusive, but equally necessary. And far from being a limitation, far from being a failure of science, I think this is one of the great achievements of human thought. To recognize that nature is more subtle than we imagined, that knowledge has limits, that reality is not a fixed stage on which events unfold, but a dynamic, relational, context-dependent process of becoming. If you're not confused by quantum mechanics, you haven't understood it properly. But if you are confused, if you find yourself struggling with the paradoxes and the contradictions, if you feel like your intuitions are being violated, good. That means you're taking it seriously. That means you're grappling with something genuinely profound, and that confusion, that discomfort, is the beginning of understanding. Not understanding in the sense of reducing the strange to the familiar, but understanding in the sense of learning to think in new ways, learning to accept that nature is stranger and richer than our everyday concepts can capture, learning to embrace complementarity as a feature of reality itself. That's what quantum mechanics teaches us. That's why I spend my life trying to explain. And that's why I hope, in some small way, I've helped you see today.